Okay, so get ready. Today we are diving into string theory.
Oh boy.
You know I love this stuff, right? And you sent over this paper, The Standard Model from String Theory. What have we learned?
Yes.
By, let me see, Fernando Marchesano, Gary Hsu, and Timo Weigand. These guys are heavy hitters.
Absolutely.
So let's jump right in. What's the deal with string theory?
Well, string theory tries to answer one of the biggest questions in physics, which is how to combine quantum mechanics, the physics of the very small, with general relativity, Einstein's theory of gravity for the very large.
Right, because those two don't really seem to get along very well, do they?
They don't. And string theory says that maybe the universe at its most fundamental level is not made up of point particles, but rather these tiny little vibrating strings.
Okay, so instead of picturing like Legos, it's more like everything's made of tiny little, I don't know, guitar strings
Yeah, you got it.
vibrating in different like frequencies or something like that.
Exactly. And much like a guitar string, if you excite it in different ways, it produces different notes. So string theory says that the different vibrations of these strings give rise to the different particles and forces that we observe.
So it's like the universe has a built-in symphony
Yeah.
and each particle is like a different note.
Yes, that's a nice way of putting it.
I kind of like that.
Right.
But it gets weirder, right? Because this paper is suggesting our universe might not be the only one. We're talking about a landscape of universes.
Yes, that is one of the consequences of string theory, this idea that our universe is not unique, that there might be countless other universes out there with different laws of physics.
So instead of one universe, now we're dealing with like infinite universes,
Yeah.
each with their own set of physical laws. Okay, so let's bring this back down to Earth for a second.
Okay.
We have the standard model of particle physics. That's our best understanding right now
Yeah.
of the fundamental particles that make up, well, everything.
Yes, that's right. And what's amazing is that string theory, even though it's so complicated, it actually can reproduce many features of this standard model.
So it's like string theory can speak the same language as our current understanding.
Yes, it can explain the same phenomena, but at a deeper level. For example, the standard model describes these fundamental forces, like electromagnetism or the strong force. String theory provides an explanation for these forces based on these tiny vibrating strings.
So it's like string theory is giving us like a deeper layer, like under the hood
Yeah.
of what's actually going on.
Exactly, yeah. And even the particles themselves, like electrons and quarks, these fundamental particles, they can emerge naturally within the framework of string theory.
Okay, so we have these tiny strings vibrating away. They're creating these particles and forces that make up our universe.
Yeah.
But you mentioned earlier something about extra dimensions, right?
Yes. Yeah.
And I see this paper really dives into this thing called compactification. What is that?
So that's where it gets really interesting. String theory, in order to work mathematically, it needs more than just the three spatial dimensions that we experience in everyday life. It needs extra spatial dimensions.
Okay, there's like up, down, left, right, forward, back.
Exactly, but string theory says we need more, but these extra dimensions are curled up so tiny that we can't see them.
They're like hidden.
They are hidden from us, yes. And compactification is just a way of describing how these extra dimensions are curled up, how they're hidden from us.
So they're tucked away so we don't even realize they're there.
Yes, exactly.
But this paper is suggesting that they're not just passive, they're actually affecting how our universe works.
That is precisely it. This is where it gets really interesting. The way these extra dimensions are curled up, their shape, their geometry, actually influences the physics that we observe in our four-dimensional world.
Hold it. So these hidden dimensions, they're like secretly pulling the strings. They get to decide how our universe works. I need a minute to process this. Okay, I think I'm ready. So these hidden dimensions, they're not just some mathematical quirk. They actually have a say in how our universe works.
They do. It
Yes.
turns out that the properties of these hidden dimensions could determine things like the strength of the forces that we experience, or even the existence of certain particles like the Higgs boson, which gives mass to other particles.
You're blowing my mind right now. The very essence of our universe, the forces, the particles, it's all being influenced by dimensions we can't even see.
That's right.
There's more to the universe than meets the eye. Or in this case, more than we can even perceive.
It makes you wonder about what's natural.
What do you mean?
Well, we have this idea in physics about naturalness.
Mm-hmm.
The laws of physics, the constants of nature, they shouldn't be too finely tuned, right?
Okay.
But then when you have this idea of a landscape with all these universes, maybe our idea of what's natural needs to be like reevaluated.
So it's like if you walk into a room and there's one clock and it's telling the right time, you'd be like, wow, that's lucky.
Right.
But if you walk into a room, there's a billion clocks, one of them's got to be right.
Exactly. So maybe our universe is not that special after all.
I like that. But this paper, we're not done, are we?
No, not at all.
It also mentions these things called dark sectors. What are those? Sounds kind of ominous.
Dark sectors refer to parts of the universe that don't interact with light as we know it, so they're hidden from our view.
Like a cosmic shadow world.
Yes, you could think of it like that.
So we have hidden dimensions, and now we have hidden realms within our universe.
And it turns out that these dark sectors might be connected to those extra dimensions.
Of course they are.
Because when the extra dimensions curl up, they can form these hidden sectors that only interact with us gravitationally, so very weakly.
Okay, so we've got these hidden dimensions shaking the universe, hidden sectors. Like, what's so exciting about these dark sectors? Why should we care?
Well, one of the most exciting things is that they might hold the key to understanding dark matter and dark energy.
You're talking about the stuff that makes up like 80–90% of the universe that we can't even see.
That's right.
We've been looking for dark matter particles for decades.
What if we've been looking in the wrong place? What if dark matter is hiding out in these dark sectors?
Like we're looking for our keys in the refrigerator and they're in our coat pocket.
Exactly. And not just dark matter, but dark energy, that mysterious force that's accelerating the expansion of the universe that might be explained by these dark sectors as well.
Wow. Okay, so string theory is not just about tiny strings vibrating. It's suggesting the existence of hidden worlds all around us that could explain some of the biggest mysteries in the universe.
Exactly. And what's even more fascinating is how string theory suggests ways to extend our current understanding of particle physics, the Standard Model.
Extensions to the Standard Model. You're going to have to explain that one.
Yeah, so one of the most interesting extensions that comes out of string theory is this idea called supersymmetry.
Supersymmetry.
Or CUAY for short.
So you say, sounds cute.
It does. But it's a really profound idea. It says that every particle that we know of, every particle in the Standard Model has a partner particle, a super partner. We just haven't found them yet.
So there's like a whole other set of particles out there that we haven't discovered yet.
That's the idea.
And why haven't we found them? Are they hiding?
Well, they would interact very weakly with our ordinary matter, which is why we haven't seen them yet. But if we could find them, it would solve some big problems in physics.
Like what?
Like the hierarchy problem, for example, which has to do with the mass of the Higgs boson. Supersymmetry could explain why the Higgs boson is so light.
Okay, so string theory gives us this treasure map, maybe a little bit blurry.
Yeah.
But it's pointing us towards these new particles, new phenomena that could totally change how we think about the universe.
Exactly. And the more we learn about string theory, the more we realize how much we don't know.
Yeah, we've been talking about extra dimensions, dark sectors, supersymmetry. This is a lot to take in.
It is.
But you mentioned earlier that string theory even has something to say about space and time themselves. And as you know, I'm a sucker for a good space-time head-scratcher.
Well, we normally think of space and time as separate, right?
3 dimensions of space, 1 of time, like a cosmic grid.
Exactly. But string theory suggests that the separation might be an illusion.
Okay, hold on. Are you saying that space and time as we know them, they're not even real?
Think of it like this. Imagine you're looking at a smooth sheet of paper. From a distance, it looks two-dimensional, right? But if you zoom in really, really close, you start to see the fibers, the threads that make up that sheet.
Okay, so you're saying that our everyday experience of space and time, it's like that smooth sheet of paper. But if we could zoom in to the Planck scale, the tiniest scale imaginable,
That's where string theory comes in.
we'd see that it's not smooth at all. It's actually woven out of strings.
Exactly. Space-time itself might be an emergent property arising from the interactions of these fundamental strings.
So space and time, they're not the fundamental building blocks we thought they were. They're more like side effects.
In a way, yes.
That's a lot to process. So to our listeners, if you're feeling a little overwhelmed right now, that's okay. We started with this paper, what have we learned from string theory? And it turns out we've learned a lot, but we've also learned that there's so much more to learn. The universe is a mysterious and wonderful place, and string theory is leading us to some of the most profound and mind-blowing ideas in the history of science. So until next time, keep those questions coming, keep exploring, and keep looking up at the stars.